In Chapter 10, we're going to look at alkyl halides and how to prepare them from alcohols. We already know that we can prepare alkyl halides by doing a free radical halogenation. If you recall, we take an alkane, and so this RH is representing an alkane, and we mix it with bromine or chlorine and a free radical generator, or we use light. And what happens is the free radicals then allow the alkyl bromide or the alkyl chloride to be made with a side product of hydrobromic acid or hydrochloric acid. And we found that it was more likely that you would find the bromine or the chlorine on the more substituted carbon, and this was due to stabilization of the free radical by the alkyl groups. So tertiary was most likely to have substitution, then secondary, then primary. Well, we're going to add that allylic free radicals are even more stable than tertiary free radicals. And what we're going to do is look at something called NBS, or N-bromosuccinimide, as a generator of bromine in situ. So here is N-bromosuccinimide, and we just usually use this acronym NBS over the arrow. We require light and carbon tetrachloride, which is just a solvent. It doesn't do anything but help dissolve everything. And when we mix NBS with an allylic, something that has allylic hydrogens, what we find is it's preferentially brominated at those positions. Why is it preferentially brominated there? Well, first of all, the allylic position is a more stable free radical, so this free radical forms faster at these two positions. The other thing is when we use NBS, NBS generates very tiny quantities of the bromine free radical. And when we use NBS, this tiny quantity of the bromine free radical that's generated is more selective than when you have a huge quantity. So by giving just a tiny quantity of the bromine free radical, we increase the selectivity. Now, just to review free radical stabilization, what is the most stable free radical? Allylic or benzylic, either of those, where you have the free radical adjacent to a pi system, is most stable. Then comes tertiary, then comes secondary, then primary, then methyl, and the lowest of all is when it's on the double bond itself, that we call vinylic. So keep all this in mind as we go to do reactions. This is showing you the resonance between the two different ends of the allylic free radical. Here is an allylic free radical because the free radical is adjacent to the double bond. What happens is it's able to undergo resonance so as to spread out that free radical, and it thereby stabilizes the free radical so that it is more stable. So we can use this to make dienes. We have already learned that when we have an alkyl halide and we treat it with potassium hydroxide, an E2 reaction occurs and we get the alkene. It's the more substituted alkene. Well, what we find is NBS will put a bromine adjacent to the double bond in this allylic position. If we then treat with potassium hydroxide, we get what is called a conjugated diene. That conjugated means that it's double bond, a single bond, and then a double bond. And 1,3-cyclohexadiene is an example of that. Here's an example. I can take cyclopentene and treat it with NBS, carbon tetrachloride. Remember, the carbon tetrachloride is just a solvent, and light. That's what H nu stands for, is light. And what happens? We get bromination in the allylic position. Here's another one. There's two allylic positions here. Where is it going to brominate? Well, you actually get both positions brominating. The one which you would have most likely occurring would be over here because that is a secondary carbon as opposed to a primary one. But you actually would get both of them forming. Here is N-bromosuccinimide being used with cyclopentadiene. Where's the allylic position? Figure out where bromination will occur. Of course, the allylic position is right here and the bromine would form there. What about cyclohexadiene? This is 1,4-cyclohexadiene. Where would bromination occur? Yes, bromination would occur in the allylic position. In both of these compounds, you only have one allylic position, and so you only get one product. In this chapter, we're going to learn how to actually prepare halides from alcohols. There are two sets of reagents that we can use, and which set depends on what type of alcohol we have. If we have a tertiary alcohol, what we find is we can use hydrogen chloride or hydrogen bromide gas, and we can treat the alcohol with that it's a hydrogen bromide or hydrogen chloride, and it actually protonates this, that leaves, and then we get the halogen coming in and substituting on the carbon. This reaction works very well with tertiary alcohols, but it does not work well with secondary and primary or methyl alcohols. Why? It's because the mechanism of the reaction involves a carbocation, and tertiary carbocations are more stable than secondary, primary, and methyl. So this reaction is very fast and easy for a tertiary, but with secondary and primary, the formation of the carbocation is slower, and the carbocation is prone to rearrangements. To prepare halides from primary and secondary alcohols, what we do is we use thionyl chloride and pyridine. The pyridine is just a base. It's an organic base that removes hydrochloric acid that forms, or we use phosphorus tribromide. Here's an example. This is a secondary alcohol. It's called cyclopentanol. We treat cyclopentanol with phosphorus tribromide, and what do we get? We get the alcohol being replaced with a bromine. Here's a couple eutriates for you. What's the reaction of 1-hexanol with thionyl chloride and pyridine? The product of this reaction is going to be rather straightforward. You just take the alcohol group and you replace it with a chlorine. And we get this product. Notice this would not work if it was tertiary. This reagent only works if it's primary or secondary. If it's tertiary, you have to use hydrogen chloride. So what's the product here of 4-methyl-2-pentanol with phosphorus tribromide? The product of this reaction, because it's secondary, will work. And so what happens is the alcohol is replaced by a bromide. And we get 4-methyl-2-bromo, or I guess 2-bromo-4-methyl-pentane. What reagent would you use here to change 1-methyl-cyclopentanol to 1-bromo-1-methyl-cyclopentane? Because this is a tertiary alcohol, you'd have to use hydrogen bromide. What about to change cyclohexylmethanol to bromomethylcyclohexane? Because this is a primary alcohol, you would have to use phosphorus tribromide. So, for a tertiary alcohol, use hydrogen bromide, and for a primary alcohol, you would